Good morning, all. I hope you can hear me. And let me first say that it is an absolute pleasure to join you at this conference this morning. The topic of the future of the internet is one that I've been keenly interested in for many years. And I hope you will enjoy the opportunity to share a discussion on this topic, both in this session and in the coming panel sessions across this conference. So with no further ado, I'd like to share my screen and proceed with some quick opening thoughts about what we mean about the future of the internet, and in particular, think about what the needs are of the internet over the coming, let's be big, couple of decades, 30 years, maybe longer. The internet is certainly now not recent. It's quite old. The early papers on packet switch networking using the architecture of the internet. The first paper was by Vince Cerf and Bob Kahn in 1974. So that's just under 50 years ago. So this is not recent. The early days of the internet was as a relatively small scale research project. And what it was doing at the time was connecting up computers. But the computers at that time were not the computers that we're used to today. They weren't handy little things that fit in your pocket. They were dramatically large pieces of steel and iron with huge power supplies, air-conditioned rooms, a whole group of computer operators to tend their every need. Here I found, and it's not easy these days, a picture of a digital VAX 11780. I actually used to program on them. It was one of my earlier jobs. And this is a small one. It's only got a mere 6 cabinets. Others were up to, 10, 15, 20 cabinets deep. So these computers were big. They performed everything. They were the server and the client. They were everything. The network was merely a packet transmission facility. And it was perhaps one of the worst packet transmission facilities we'd built because it wasn't reliable. When one of these computers passed a packet into the internet, it was not clear that the packet was going to make it to the other end. Networks were allowed to drop the packet. And when we placed 3 packets in order into the network, we were allowed to deliver them in a different order. And so in some ways, this is the world's worst network. What was going to fix everything up, however, wasn't the network. The network wasn't going to correct its own problems. It was the devices at the end, these computers, that were going to fix everything. So it was this principle of a cheap, dumb network. And I emphasize the word cheap. It was cheap. And the computers were actually incredibly smart. The protocols that drove these packets were the key protocols that made the internet work. And so all the functionality was pushed to the edge. Now, this didn't last long, oddly enough, because computers kept on changing. And one of the ways they changed was in the 1990s. And again, I've dragged out a picture of a relatively early personal computer. Now, these were relatively dumb devices. The operating system they had, things like MS-DOS, and even the early versions of MacOS weren't exactly fantastically clever operating systems. They couldn't easily be used as servers, nor do we want them to. because we were selling these computers as consumer devices into a far bigger market, far bigger than a few thousand university networks, a few thousand research institutions. No. Personal computers, we were selling millions, tens of millions every year. And we viewed these computers as clients, as customers, not as servers. And so we started to create a two-speed internet, where what we had were these personal computers at the edge who really were customers of the internet, and pulled other functions that used to be done on the larger computers, oddly enough, right into the network. And so what we did was pulled things like the internet's naming system, the domain name system, which, by the way, is about to turn 39 in a couple of days. We've had the DNS for many years now. The routing system, which again was performed by mainframes, is being pulled right into the network. And a whole lot of other services, messaging, content, and so on, all became network services. And so the network started to beef up, and the computers at the edge started to dumb down. And we had this asymmetric client-server network. The clients connected via thin wire modems. You'd be lucky to get more than 20 or 30 kilobits per second. This was not a fast network. Whereas the servers, which connected deep into the network, were actually connected at better speeds. But even so, it was finding difficulty. The network, as we built it, wasn't coping. And so we progressed by creating more specialized structures inside the network. We started to build a structure of connectivity so that every region, and often every country, actually had exchange points where all the local service providers met at the same facility and exchanged traffic in order to eliminate long and inefficient paths through the network that simply created delay and trouble. We built peering points, we built gateways. All of these systems were designed to improve the performance of the internet and reduce things like latency and increase the usability. Even so, we never had enough capacity. We had more demand than we had network. And so there was a huge amount of work on engineering traffic through this network to make sure that we could actually use paths that existed rather than sending all the traffic into one large black hole. And so quality of service engineering, trying to equip the network with ability to actually treat packets differentially. Some packets were more important than other packets. And when there was a large amount of congestion, quality of service was meant to dictate which packets would get dropped first and which you try and keep hold of. At the same time, we stopped distributing services across the network and moved them back into specialized centers, what we now call data centers. And certainly by the late 1990s, we started to get into the habit of building data centers to host our services. At the same time, we started specializing the internet so that one network platform was meant to meet a whole bunch of very, very different application sort of realms, very different customer sets. And they didn't like sharing clearly. They didn't like to have their packets at the same level in the network as everyone else. And so we started doing network segmentation, and virtual private networks was a very, very big feature of the late 1990s, early 2000s. And at the same time as well, we had a real issue with scaling, in particular scaling, forwarding and routing. So we borrowed an approach from the asynchronous transfer method, ATM, and using that kind of cut-through switching, started to do label switching in the internet, MPLS, or multi-protocol label switching. As you can see, as we try to make the network bigger and more capable, we end up adding services and functions directly into the network itself. This is no longer a dumb network. These are not simple packets anymore. The network itself is trying to take charge of the entire service environment, and everyone else, if you will, is treated as a customer. It's almost a rebuild of the old telephone network architecture. At the same time, we stopped using just wires. Mobility, which was a very big thing in telephony, also took over the data world. These days, I would guess around 80 or 90% of all services on the internet eventually go to mobile handsets. Almost everything is mobility, and the wired network is becoming harder and harder to find. And as we scale up, what we're finding is we're actually building different kinds of networks for different roles. So we're building customer access networks to feed customers to concentration points. We're building content distribution networks to farm content out. And all of these are quite specialized networks and actually have very little in common with each other. And I suppose you could say, and you'd be right, that they're all different. They're all very, very different networks. Now, if we were doing this in the 1970s, 1980s, possibly even in the 1990s, each time we invented a different kind of network, we'd actually build an entirely different networking protocol family. ATM was an entire protocol suite designed to solve a particular problem. Even when the Ethernet cable system first came out in the 1980s, Digital, who was one of the Digital Equipment Corporation, who was a great proponent of Ethernet, built a whole suite of protocols and services based solely on Ethernet and its properties. So every time we pulled out a new communications technology, we needed to invent and rebuild an entire suite of software to actually handle that technology. This is expensive. This actually stops things from changing, because each time you try and introduce a faster technology, you have to introduce an entire landscape of networking to build on top of it. The genius of the internet was that it didn't tie itself to any particular technology. The first large-scale national internet, the National Science Foundation network of 1988, was originally built using a set of backbone links that operated at 56 kilobits per second. Not megabits, not gigabits, not terabits, 56,000 bits per second. Now, today's internet is much the same as that internet protocol of 1988. It's still a basic packet forwarding datagram technology, and the packet headers that we use today are the same in version 4 as the packet headers we used in 1987. Same technology, but now we run that technology over links that these days, gigabits, 1 or 2 is common, 10 gigabits is common, 100 gigabits is our general fodder for networking. And we're now pushing forward beyond 800 gigabits per second into looking at 1.6 and even 3.2 terabits per second using the same technology, the same internet. And this, of course, preserves the value of the investment. We've never reinvented any of the other protocols as we keep on upgrading the underlying substrate of networking itself. So that's a quick potted history over the sort of last 40 odd years of the internet's technology and evolution, the factors of change. But we didn't come here to talk about the past. We come here to talk about the future. What can we say about the coming decades? Well, it's pretty easy to actually say that certainly in the coming decades, most of what's going to happen is already with us today. It's already there. The problem is lots of other things are there as well. And the real challenge is to get rid of the things that are distracting and actually figure out what's been important, what's going to drive change for the future internet. So I think there's one thing that has really, really driven our thinking, particularly in the last 10 years, has driven the way we look at technology. And oddly enough, it's a change from scarcity to phenomenal abundance. This device is a supercomputer if you use the metrics of 1987, probably larger than the largest computer we could build in 1987. We're finding that we're building literally billions of high-speed processors every year and pushing them out into the world. Compute power is not scarce. Memory is not scarce. Storage is not scarce. And if we actually have a look at the underlying medium of pushing bits through wires, in fiber optic cable systems, we're now able to push, as I said, hundreds of gigabits per second. The total capacity of the world's network is probably in large numbers of petabits per second. This is not a network that is constrained by scarcity. 5G systems, which are being rolled out for the mobile world, are now looking at itself at gigabits per second to every handset. So we're now looking at a network that is being driven with abundance. And that's a different thinking, because all of a sudden, when you're in a scarcity mode, you have to think about rationing. You have to think about sharing. You have to think about limiting some demands to allow others to surface. You have to think about making this scarce resource available for everyone. In abundance, you don't have to think about that. You've actually got to think about something quite different. So the factors that are driving us now are actually factors about, firstly, making the internet bigger, a lot bigger, very, very quickly. The transmission folk, particularly in the fiber world, have been working extremely hard. And by and large, fiber exceeds silicon in capacity these days. 10 years ago, we were using simple fiber systems that blinked on, off. That's old hat. We're now using systems that can change the phase, the amplitude, and the polarization. And so we're now able to drive systems that in a single fiber pair can run up to 1.6 terabits per second in just one fiber pair. And we're laying subsea cable systems with 16 of these fiber pairs, each capable of 1.6 terabits per second. All of a sudden, we have enormous amounts of transmission capacity around the entire world. At the same time, servers are cheap. If you go out and want to rent a server, you can get an astonishing amount of compute power for a few small dollars a month anywhere in the world. So all of a sudden, servers aren't difficult and scarce. Servers and content is everywhere. And at the same time, mobility has been matching that we're now getting mobile networks that literally are everywhere. And so oddly enough, a bigger network has changed the way we think about the network. Instead of putting up a server and people connecting to it, we don't do that. We take those services and content and push them to where you are, to where we exist as customers. And so the network doesn't bring users to service and content. Whatever network we have in the middle pushes it out to the edge, and all we see as customers is that single transaction across the edge of the network. Because in the middle, these content networks have pushed it out already. Caching is your friend when you have abundance. Now that is dramatic. Why? Because by making the service closer to the user, it's faster. It is so much faster to serve from a couple of kilometers away than to push your packets around the world with the extraordinary delays that entails. Fiber is not that fast. It still takes a fifth of a second to move from one part of the world to the other, and sometimes longer. If we can bring the content close to the user, it's not a fifth of a second, it's 5,000ths of a second or even less. That's fast. And we've built specialized networks, content distribution networks, to push all this content out so that we can do this. So if you think about the amount of distance your content has traveled to get to you these days, it's not a few thousand kilometers anymore. When we were doing work in Telstra in the late 1990s, we calculated that around 70% of all the traffic that we delivered to Australian users had come across the Pacific. In other words, the packet miles was up around 5,000 miles for 3/4 of the content. If you did the same exercise today in Australia, I think you'd find that the average distance packets travel to deliver content to users has shrunk to certainly under 100 kilometers. And my guess would be closer to 10, 15 or 20 from 5,000. Now, if distance is cost and distance is speed, that's incredibly fast. At the same time, faster fibre, as I've said, and faster cellular data, 4 gig, 5 gig. So all of a sudden, this is a really, really fast network. Higher capacity circuitry and compressed interactions across shorter distances mean we don't now wait for the network. Waiting is bad. It's a swear word in internet engineering. Fast is what we're chasing. Every last millisecond counts. We've also been improving by using abundance of computing. We've been improving trust in the network. Encryption is now ubiquitous. Chrome is about to stop serving unencrypted port 80. We're moving to a world where everything is encrypted. Even that last portal, the TLS portal in Transport Layer Security, the unencrypted server name indication is going away. Apple have just released for the mass market a version of oblivious web fetching in its private data relay service. Nobody, not even the network, can work out who is fetching what data, because in that version of oblivious web fetching, HTTP, we're doing double layers of encryption to actually isolate knowledge of the querier from knowledge of what is being queried. So it's a better network because we stopped trusting it. All trust is now up in the edge, in the application. And the whole question of whether a network is trustable or not doesn't matter. We assume that all network infrastructure cannot be trusted and should not be trusted. And in essence, the applications are saying everything is encrypted, there is no information leakage. And that's been a dramatic change over the last 10 or so years in the entire world of the internet. Now, abundance also drives another thing, which is price. And price has been plummeting. There are a couple of reasons for this, and one is, of course, economies of scale. We talk a lot about big tech. We talk a lot about the 5 or 6 giants that run this industry, and that's true. On the upside, those 5 or 6 giants can do things at an economy of scale that smaller players can't. And that actually creates a far cheaper service for consumers. Yes, it's not all good, but at the same time, if making things affordable is what we wanted, we're certainly getting there. And oddly enough, we've even gone to free. How do we make things free? Well, interestingly, I can't sell my profile individually. I can't sell to advertisers what I intend to do. I'm too small. But oddly enough, Google, and these days Amazon, and Meta, all create a profile of me and a few 100 million of my cohort. And they sell that information, those profiles collectively, for a large amount of money that funds all these services. Google search, funded by advertising. Gmail, GDocs, all of Facebook, all of Twitter, funded by advertising. So oddly enough, this stuff is dirt cheap by basically capitalizing an asset that you and I both have, but we can't sell it ourselves. They've aggregated and sold that to create a service that is basically free. And oddly enough, we've now built luxury. We've now built the best we can build. And instead of making it available to a few rich people, it's now available to everybody as a mass market commodity service. So we've kind of achieved the impossible, haven't we? This network that we're looking forward at was already starting from being bigger, faster, better, and cheaper. All good, right? Well, maybe not. And there's certainly things to think about as we move forward, because we have subtly changed a bunch of things. And there are 4 here that I've called out that I think are important. For almost as long as I think all of you, and possibly I, have been involved in the technology of the internet, we've been battling with address scarcity in IPv4. We'd only just got started with the internet in 1990. We'd only just started rolling it out when Frank Solinsky turned up at an IETF meeting and said, "Party's over. We're about to run out of addresses in V4. Time to do something." We thought at the time that this was going to be a panic moment. And so we panicked. We very quickly worked on a new protocol, amongst other things, and devised IP version 6. We expanded the address space to accommodate the breadth of silicon. 2 to the power 128 is a very big number. We felt confident that we could provide an address to every endpoint. Yet, did it matter? At the moment, we have about 50, maybe 60 billion devices connected to the internet, and all of them speak V4. Only a third speak V6. So we have about 60 odd billion devices connected into a network whose address space is only 4 billion big at most. Somehow we've managed to do the impossible. How? Because we've changed the way the network works. And addressing is now no longer absolute and persistent. Addresses are just ephemeral conversation tokens. We share them. Network address translation is now everywhere. And oddly enough, what that's meant is that addressing is no longer a critical aspect of today's internet architecture. Why have 2/3 of the world not embraced IPv6 yet? Because addressing is not an intrinsic necessary part of the internet architecture. So that's a very big change. Will we go back and revert to using that architecture in an all IPv6 internet? I don't know. But it's worthwhile to look at that at the same time as we've done that, we've also evolved in terms of names and namespaces. The DNS has moved an extraordinary long distance from where it was 39 years ago. And you've got to wonder if names are actually more important than we thought. Names are actually the lingua franca of the network. It's not addresses, it's actually DNS names. Because now we're using the DNS not just to translate a name to an address. That's old hat. We're using the DNS to map a service to a rendezvous point. The recent work in the SVC work in the IETF and the HTTPS work in terms of creating DNS objects that don't just tell you the address of a service, they tell you what protocols to use. What application level should I use? Should I use UDP or TCP? What encryption keys should I use? All in a single DNS query. So it's actually the DNS that is becoming the referential rendezvous point. A single query will tell you how to get to somewhere. And so all of a sudden, we're no longer an address-based internet, we're a name-based internet. And then we sort of think about what's the nature of network transactions when the same content is everywhere. You can go to APNIC's website, I can go to APNIC's website. The server that responds to me is located probably in maybe Brisbane, maybe Canberra, maybe Sydney, but I know the server that responds to you is somewhere much, much closer to you. Different server, same service, same content. So what's the nature of a network transaction? Well, we're both doing the same thing, but with completely different endpoints. What defines the fact that it's the same service, even though all the elements are different? So what's the longer term trend? For the last 40 years, we've been obsessed with routers and wires and cables, all the transmission infrastructure of a network, all that sharing technology. Packets are a way of sharing a common underlying network. We don't need to do that anymore. Transmission infrastructure is abundant. We don't have to bring consumers to service delivery points. We bring services towards consumers. Infrastructure doesn't matter. Applications are now taking over. And now what's happening is it's the software that matters. It's the software where we're doing the most innovation and not the hardware. The application is the new service of the future internet, not the silicon itself. And so interestingly, the last question that I will leave you with is perhaps the most provocative. The networks matter because we've actually stripped out a whole bunch of functions we added in the 1990s. In our search for cheaper, faster, more flexible, we actually got rid of all the things that we built in, the MPLS, the QoS, the VPNs, etc. We've got rid of that. Everything is on the edge. Everything is off the network. All that's left inside is actually a collection of dumb wavelengths run by folk like Microsoft Azure and Google and Facebook. They're not shared with you and I. We don't send our packets around the world anymore. We just use the last mile to get to the local data center, and that's it. So if you think about this, what defines the internet? Is it what it used to be in the 1980s, a shared transmission fabric, a suite of protocols, a common address pool? No, that's not the internet. The internet is actually a completely disparate set of services that shares a common referential mechanism. I can talk about my web page and you can see the same thing I'm seeing. I can talk about my bank, things that matter to me in reference terms that matter to me, and I can share them with you and you will see the same thing. The technology of how you get there might differ between you and me, but that doesn't matter. Because what we really wanted was a common way of communicating shared referential points. And with that, I would like to leave you with that thought, and hopefully that will give you some sustaining interest over the coming conference to think about the future in very, very different terms to the way we've thought about the past. Thank you very much.